Explain why, although the speed of the satellite is constant, the satellite is accelerating. Because it's constantly changing direction.
Mm-hmm. So velocity is a vector. So vectors have an angle and a magnitude. If the magnitude stays the same, well, the vector can still change angle. And if it's changing angle, well, that means there must be an acceleration.
Mm-hmm. Yeah.
So good.
Discuss whether or not the gravitational force does work on the satellite.
Does work? Interesting question.
Work as in what was the energy over time, I think. Yeah. Is work done, or like energy over time? It doesn't mean work as in the equation, or work as in like is it functioning? Like is the actual
As in the physical quantity of work, as in yeah, like the actual. There's an equation for this, by the way.
MGH.
No, that's MGH is potential energy, right? I mean, it can become work, but that's like a small step after, right? So there's actually an equation. I'll share it with you. So let's say you have a force, right? Let's say you have a block, okay?
Yeah.
And let's say this block is on a some surface, okay? And let's say I push this block. So I push it this way with some force, okay? The work that is done on this block, if you think about it, is energy, right? It's some type of energy. So we know for a fact that work will have joules as a unit. Joules.
Yeah.
Okay, but what are joules? What are joules? Joules is the same thing as Newton times meter.
Yeah, Newton per
right?
meter.
So really, if you think about it this way, you can say this is a force times the distance traveled in the direction of the force. So this block is going to move here, okay? And then the work done would be, so you have some distance here, d. Let me use a better color. And so when we talk about the work done on this block, it's the work is equal to the force times the distance in the direction of the force. So let's say if you had a distance here, then the work done would only be the part of this that is in the direction of the force. But it wouldn't make sense for it to be like this because the force is only horizontal, right? So
yeah.
Oops. So yeah, so in this case, all you really need to know is that work equals force times distance in the direction traveled. Or yeah, distance traveled times the force in the direction of the distance traveled. Okay. So if I ask you now, discuss whether or not the gravitational force does work on the satellite, how would you relate this concept of work with circular motion to figure this out?
Well, the distance is from Earth to the satellite, and the force would be 9.81. Or yeah, it would be.
Well, it wouldn't be 9.81. That'd be the acceleration, but because you have to take into account the mass of the satellite, right? But that's not given to you. So what you should do, first of all, when you have a force problem, draw a free body diagram. What is the body of interest here?
The satellite.
Okay, so draw, like, you can write a dot if you want, and that would be like the point mass of the satellite. Yeah. And so if you draw all the forces on the satellite, what are they? What forces exist?
So one would probably be pointing towards the Earth, which is gravitational pull from the Earth. So I'm just gonna call it just G. There should be another one here as well, which is.
So you should probably write it as FG. This is the convention, at least, because G could be the constant G, right? And that could get confusing.
Yeah. And it should be acceleration as well when it goes around.
So let's say, okay, so you drew a gravitational force, and what is this arrow here?
Centripetal acceleration.
So centripetal acceleration. So I'm not sure what you mean by centripetal acceleration.
No, wait, hold on.
I mean,
it's like, it's already going. No, hold on.
figure it out.
Yeah. Does mass have anything to do with it? To do with it, or rather?
So here's the basic thing. So the first thing, right, is, let's say it's a satellite and it has some mass, right? It has mass. So what are the possible forces that could be affecting the satellite? Well, the satellite is an empty space, right? There's no friction, there's none of that. There's Earth really nearby. So you could say very correctly, like you did, is that there's an FG. And if we just draw, I'll use your diagram. We're going to draw this circle. Okay, this is the circle that the point is traveling along, right? So we know that this point is always on this circle. Okay. So what we know is that it's either going up or down in terms of velocity. So these are velocities, though. They're not forces. Okay, so it's either going this way. Actually, it's telling us it's going this way. So we know that the velocity is going to be here. Okay. We also know it's in circular motion. So in terms of the forces, the gravitational force is one of the forces we could write, but there aren't really other forces, because what are the forces? So there's gravity, then there's the magnetic fields. There are no magnetic fields here. There's no friction. There's no reaction force. There's nothing, right? So really it's like 2 points. If you think about it, the Earth is some mass in empty space that's just big. And then the satellite is just a really tiny point in empty space. And so really the only connection between these two objects is the force of gravity. There's nothing else really bringing them together or apart. So in this case, the force of gravity, like you said, is going towards the center of the circle. And so there isn't really only. Yes, so that's the only force. Now this particle or this satellite is still moving, right, in a circle, but this is just the velocity. There's no actual force in the direction that is this way. There's no force. And whenever you see force, okay, I want you to think F equals ma. Every time you see a force, think F equals ma, which means if there's a force in some direction, then there is an acceleration in the same direction. If there is no force in that direction, then there is no acceleration in that direction. If there's an acceleration in the direction, then there's a force in that direction. If there's no acceleration, then there's no force in that direction. So force and acceleration are the same thing with a constant of mass. And the mass is just a property of the object. Okay. So when we look back at this circle and we look at this force, we say, okay, there's one force and it's going towards the center of the circle. Therefore, clearly we can say that there's an acceleration towards the center, and that happens to be the centripetal acceleration that you were talking about, or the normal acceleration. But if we look now at our relationship or our definition of what work is, so work we defined as force times distance traveled in the direction of the force. And so if I asked you now, is the satellite moving in the direction of the force at some point in time, what would you say?
Wait, could you repeat the question?
If I asked you, is the satellite moving in the direction of the force at any time or at some point in time, is that true or false? Is there any point in time where the force and the direction of the motion are in the same direction?
No, because if the satellite were to orbit around, it has to keep going in that orbit. It can't just fall inwards.
Exactly. So the force, we're saying the distance traveled is let's say in the bottom direction in this case, but the force is towards the circle. So do you see how these are? If we draw these two vectors, so this is the force vector, this is the the velocity or whatever, the distance vector or the velocity vector you want to think about. And you see how there's like a 90-degree angle between them? So if you do F dot, because this is actually a dot product sort of, because it's FD cos theta, right? That's really what it is. Theta here is 90 degrees, therefore cos theta is equal to 0, right?
Yeah.
So that means that there's no work done on this satellite because the force is always perpendicular to the motion of travel. So the force is not doing any work. Does that make sense?
Oh, okay. I see.
Mm-hmm.
So the force is completely perpendicular towards the Earth, and then if you do the FD cos theta, cos 90, which equates to 0, W becomes 0. Oh, okay, I see.
Exactly.
Yeah.
And so if you look, if we put it here, well, the force is always going to be towards the center, and this velocity vector is always going to be tangent to it. Tangent should imply as well that it's 90 degrees. But and so it will never have any work done on it.
The work done is always 0.
Yeah. So when they ask you, does it do work on the satellite? You say no.
Okay.
Is that, you get it, right?
Yeah, I got it.